Good morning, everyone. I hope you're having a good time. Yeah. I think it's time to start our the first lecture of the Astrophysics series. Today we have Manuel with us. He's going to talk about formation channels and a little bit about populations, I guess. Yeah. So take it away.
Good morning, everyone. So this is a kind of pretentious title for a 1.5-hour lecture. So let's see what we are going really to do in the next minutes. We will have like a crash course, very fast, very brief, on the formation of compact objects from stars and the way they pair together and may contribute to the gravitational wave astronomy thing. So generally, stars are big bubble of gases whose evolution is determined mostly, in a very simplistic way to say that, by their mass. So we have stars with a mass below 0.1 solar masses around, which are too light and too cold to ignite the hydrogen, and this means that they are just doomed to die as brown dwarf. They actually are more closer maybe to a planet than to a star. And then we have low massive stars, subsolar objects that manage to ignite hydrogen. They convert hydrogen into helium. Helium accumulates, but cannot be ignited. The temperature attained by the star and the densities are not enough to ignite helium. So the star, after a red giant phase, slowly cooled down as a white dwarf, helium-rich white dwarf. A bit more massive stars, from Sun till 6 to 8 solar masses, the star undergoes several phases up to the formation of carbon and oxygen in the core. So they ignite helium once they form, and then the helium is ignited, carbon and oxygen are produced, and you have a layered structure in the star with the hydrogen in the outer layer, and then helium, and then carbon oxygen. And you cannot ignite carbon burning, so then the star cools down as a carbon-oxygen white dwarf. More massive stars, more exciting life, up to 20 to 40 solar masses, stars undergo a red giant phase, a blue supergiant phase when the star inflates during the stages where more heavy elements are burned, up to a point where an iron core is formed and new nuclear reactions cannot help anymore. So the structure of the star collapses down, and the final structure during the collapse can be either a neutron star or a black hole. And then, going up in mass, after the blue supergiant phase, the star loses its envelope and can undergo a phase that is called Wolf-Rayet star, where you basically see the core of the star, which is helium-rich, an helium-rich object, and then eventually, depending on the mass, either the star explodes in a peri-instability supernova, we'll talk a bit more about that in a minute, or directly collapses into a black hole. So these are the diverse pathways through which stars evolve in a very brief and simplistic way. And each of these star subpopulations evolved through different time scales. So subsolar objects, substellar objects, the one that couldn't ignite any nuclear reaction, they are long-lived objects that cool down over a time scale of 100 megayear. Interestingly enough, the more massive the star, the shorter the lifetime. Nuclear reaction proceeds at a higher rate, and this shortens the lifetime of the star, up to a point that while solar-like stars live for about Hubble time, or at least a few gigayear, when you reach out, the more massive stars in the mass spectrum up to 100 solar masses, the lifetime of star is reduced down to a few megayear. So this means that, statistically speaking, if you have a stellar population, it's more probable for us to see small, long-lived objects rather than young, massive stars. But they are very interesting. Let's see why. So generally, the outcome, the end state of stars, can be more or less summarized in this way, where you have the initial stellar mass and the final product. So below 0.1, 0.08, you have substellar objects, which can be interesting to someone, let's say. I'm sure someone is interested in that. Then up to 8 solar masses, we have white dwarf, and then we have neutron stars, black holes, then we have a gap, and then possibly black holes that are more massive than 100 solar masses, which we usually refer to as intermediate mass black holes. Now, this taxonomic definition actually can be brought into more cold numbers if we couple the lifetime of stars and their evolution to some discussion about what is the population of stars. And generally speaking, if we define an initial mass function for stars, which tell us what is the probability for a star to have a given mass, phi of m, and we integrate over the entire range of masses, we could get the number of objects composing a given stellar population, right? Now, if we limit our analysis to a given mass bin, like we are doing here, or there, and we divide by the integral over the entire mass of ranges, this tells us the fraction of stars with a given mass, or with a mass in a given mass bin, right? So this tells us, out of an initial population, which amount of stars are going to be white dwarf, which one are going to be black holes. And there are several ways to model the initial mass function of stars. The most classical one comes from Salpeter from the 50s, who derived a power law function, very simple one, with a slope of 2.35. Now, there are also phenomenological power laws, mass function derived from observations of old stars in the galaxy. They are named after Chabrier or Scalo, and are all more or less our power laws or broken power laws. But generally speaking, let's see, this is the simplest way to make such a calculation. So if you substitute the power law in the integral here, you get the fraction of objects for this special IMF. And now you can just calculate it for a typical population, for example, from 0.8 solar mass till 300 solar mass, and get the number of objects that evolve into different end states. So we have white dwarfs ending up, well, no, let's say white dwarf that will become a white dwarf after a Hubble time. So they will be, but they are not yet, because they are too light and their evolutionary time scale is too long, but then constitute the 95% of objects in a given population, in the galaxy, for example. Then there is a 4% fraction of objects that will become white dwarf. And then, as you can see, numbers goes down and down as we reach the most massive objects. So, interestingly enough, the number of black holes is going to be 0.05%. And beyond that, actually to get pair instability supernovae and above all, intermediate mass black holes, you need to extend the mass spectrum. Because you get out, to get an IMBH, we will see in a moment, you need an initial mass above 100 or even 200 solar masses, actually. Yep.
Yeah, just for the neutron star, I was wondering, so before, I think the range for the neutron star was like 5 to 10 solar masses, or 8 solar masses, and now suddenly it's 1.3?
Oh, thanks. This is the final mass they attain.
So 8 is the...
Yeah, the final mass of the final product. So in this case, is the mass range they attain. So for white dwarf, we expect white dwarf to form with a mass around 0.1 or so to 1. Neutron stars are expected to have a mass around 1 and 2, 1 and 3. It depends a bit on the way you model the structure of the star. And then black holes with masses. So this is...
So the number before was the mass of the stars before.
Exactly.
Okay.
The initial mass of the star. So what we name here as the zero-age main sequence star. Yeah.
Quick. You just touched upon that, the IMBH. So prior to that, you have the PISN kind of a effect, which caps the maximum limit to like something like 40, 50.
Yep.
These IMBHs, how do they form?
So simply, if you assume that your mass function, if you assume that stars can form with a mass up to 300 solar masses, then there is a tiny fraction, that one, of stars with a mass above 230 or so that do not undergo pair instability supernova and just directly collapse to an IMBH. And we see this here. So black holes are tiny. They constitute a small fraction of objects, but have been extremely interesting in the last decade for those that, got interested in the gravitational wave thing. And the way we observe black holes now with LIGO and Virgo, and we will with LISA or with this year's detectors, what we get from the observation and the analysis of the data is a mass. We don't know the progenitor history of that objects. So we need to know how the masses of black holes look like given the mass of a stellar progenitor. This can start helping us interpreting what we are seeing in gravitational wave sources. And now, without going too much into detail, the rule of thumb is that the final mass of the black hole depends on the amount of metals present in the star. So stars are generally made up of hydrogen, fraction of helium, and then a tiny fraction of more heavier elements, which we name metals. And the amount of metals in the star determine the final end state of the star itself, the final mass of the black hole. And this is usually displayed through this kind of initial to final mass relation. So here you have the mass of the star, here you have the mass of the black hole at the end of the stellar evolution process. And different colors here correspond to different values of the metallicity, so the fraction of metals present in the star. Just for a reference, the solar metallicity is around 0.02, so it's kind of this line here, while the more metal-poor stars observed in the galaxy have more or less a 10 to the minus 4 value in metallicity. So they correspond to this purple line here. Now, when you evolve your stellar structure through all the phases of nuclear reactions and you calculate and compute the final mass of the object, for any given value of the mass, you end up with this kind of behavior and trends. And as you can see, first of all, the least the metallicity, the more massive the black holes that are produced. So more metal objects. What happens, what drives this relation is that more metal-rich objects lose more mass during their lifetime. So the star loses mass through stellar winds, and the amount of mass that is lost cannot, of course, can be converted into the black hole final mass. Metal-poor objects instead lose less mass, and then you have a larger reservoir of mass to convert into the black hole mass. This is the general, very crude idea. Now, when you get to masses of around... so as I said, in these very massive stars, what happens is that you have this nicely drawn onion-like structure, where you have hydrogen outside, and then helium, and then carbon, and then a lot of things up to iron, right? And as the star evolves toward explosion, actually, it will develop a core. Well, of course, this is not like it's stratified, but you can still have mixing, so we'll have some materials in the center. So as the star evolves, it can develop in the core helium and carbon and oxygen. And now the mass that is formed in helium determine the final outcome of the evolution. So if the mass in helium in the star is in the range between 30 and 60 solar masses around, very loose boundaries actually, because the models are very uncertain, the star, when start contracting, density in the center rises up, and the reservoir in carbon, oxygen, and silicon is ignited. So oxygen and silicon are ignited. This generates, of course, a shock wave in the star, and the star starts pulsating continuously. So you have a cyclic rebound due to the ignition of stellar product to nuclear reactions, and then a contractions due to the gravity of the star. And this leads to what is called generally a pulsational pair instability supernova. So in this case, the star loses mass over time till to a point where the structure collapses and undergo what is generally called a core collapse supernova. And the remnant, since the remnant mass is set by the mass in the core, generally attains a nearly constant value of around 40 to kind of 60 solar masses. This also, again, depends a lot on the uncertainties in the models. When the mass of the helium accumulated into the center instead is between 60 and 130 or so, the contraction phase ignites the oxygen and silicon burning, but in a so violent way that the shock wave propagated through the star just destroy it. And the star explodes in a pair instability supernova event. So no remnant is left behind. This is why you get this dip here. And as you see, the boundaries of the pair instability supernova gap are driven by the metallicity. So more metal-poor objects have a wider pair instability gap. And this has another consequence. That is, the maximum mass of objects you can form, depending on the models, is around 45 to 60 solar masses. So it's around here. You cannot form more massive black holes unless you get out of this range. So stars more massive than around 230 solar masses, let's call these ZAMs, so the initial mass of the star. In this case,
sorry,
yep.
What does ZAMS stand for?
Zero age main sequence. So every star that starts its life, we let's see this. So we can track over time the temperature of a star and the luminosity of a star. Okay, you can create equilibrium models to describe a star at the beginning of its life, after it has formed. And now if you do the calculation for the stellar structure at different masses, you will end up with the initial condition of your star. Okay? Initial condition means, in this case, an hydrostatic equilibrium model to represent a star of a given mass and with a given metallicity. And now if you calculate the effective temperature and the luminosity of the stellar model for different values of the mass, you end up with a sequence of objects. Each point on this line corresponds to a value of the mass. Generally, the smaller stars have lower, not here the direction of the temperature, lower temperatures, lower luminosities, and then more massive stars have higher temperature and luminosities. Now, as the stars, and this is called Hertzsprung-Russell diagram. Okay. So as the star evolves and starts burning its elements in the center, stars move away from, so this is called zero age main sequence. This is the locus of stars with an age of 0. And then each star, over its lifetime, moving this according to, things. Let's just skip that. So the interesting thing is that we have this huge gap in masses where we simply don't have any remnant. But then if you manage to form a star beyond 230, the ignition of carbon oxygen is not powerful enough to contrast the collapse. So the star just entirely collapses into a black hole with little mass loss. If you compare the mass of the progenitor to the mass of the remnant, you see that there is not much lost mass during the formation process. Okay, now, this carves in the diagram a hole, what is called an upper mass gap. You cannot form by a single stellar evolution black holes in this range. Yet, thanks to LIGO and Virgo and Kagra, we observed them, a bunch of them actually. 190521 was the first object leaving behind, so the first gravitational wave source associated with a black hole binary merger that left behind a black hole of 140 solar masses. And the interesting thing is not that you form an 142 solar mass remnant, but that one of the components has a mass of 85 solar masses, which is right in the gap. Another thing was out a few months ago is 231123. This is a new big champion because its components have a mass of 130 and 100 solar masses. So possibly they are both IMBHs already. And they merged, of course, to form an even more massive black hole. So the question is where these objects are coming from. Single stars is impossible. Plus, for gravitational waves to happen, you need to be in a pair, in a binary. So you need to form binaries somehow. But single stars is completely ruled out, unless you tweak your stellar models to, prevent pair instability to happen and get this mass gap higher. There are some new works that show that you can end up here with single stars. Model uncertainties, I guess. The other possibility is that the progenitors of these interesting sources have formed in binaries. And somehow they merged before. So they are the product of previous mergers. And generally speaking, there are two main formation scenarios that are classified in the field, let's say. One is the isolated binary evolution scenario, and one is the dynamical formation scenario. In the isolated binary evolution scenario, which we are talking about right now, you have two stars that born in a pair already. So from the very beginning, they are paired, and their evolution, and they generally are found in stellar nurseries or galactic fields. So their evolution is driven solely by single and binary stellar evolution processes. There's anything else that will perturb the two stars from evolving together. And interestingly enough, if we observe stellar nurseries like there, we managed to calculate the amount of objects that are in a pair out of the total number of objects in these regions. And this is work from 2017. Sorry, I forgot the reference. This is from Moy and Di Stefano. Let me just put it here. So in their work, they have shown that actually, as long as you consider, well, let me also simply say, when we have a binary, we have a primary mass and a companion. And the primary mass is generally the most massive one. Okay? So if you look at primary masses in these binaries and you calculate the fraction of these objects that are in a binary, are single, or are in a higher multiple, interestingly enough, you see that single star constitute the 60% of the objects when you consider mass bins around 1 solar masses. But their fraction reduces down to a few percent when you go toward more massive objects, which of course mean that more massive stars preferentially are found in binaries, triples, and quadruples. So more massive objects tend to form together, which means that we can study binary stellar evolution and see and try to understand whether the binary stellar evolution can help finding black holes in this gap, and more in general, forming compact binaries. And generally, it is also found that actually the primary mass more or less follows what is called the universal mass function, initial mass function, which is still a power law, but it's a broken power law. And that generally is shallower for less massive star, around 0.08, and then there's a bit steeper, and then gets a bit steeper here when you're around 2 solar masses. So this is generally an improvement over the Salpeter power law mass function we saw at the beginning. Now, to properly evolve a population of stars, especially if they are in binaries, you need to make assumptions on the way the binaries are made. This means assuming some distribution for the primary mass, like we just said, this universal mass function. What about the secondary mass? What's its mass? We can draw the secondary mass assuming some distribution in the mass ratio. For example, from observations, we see that more massive stars, masses above 20 solar masses or so, exhibit a mass ratio distribution that goes like a power law with a slope of 0.1. So if you draw the mass ratio and you draw the primary mass from the initial mass function, of course you can get the companion mass. And now we have M1 and M2, right? Because Q for stellar models is defined as M2 over M1, with M2 being smaller than M1. So this is a number in the range 0 to 1, roughly speaking. Yeah. So if you draw the primary mass, you can get the secondary mass from the mass ratio. Once you have the two stars, you need to decide how much they are separated. Yeah.
Sorry. It seems there's sort of like an implicit assumption that you don't have mass ratio less than 0.1. Is that because in the isolated binary evolution you generally...
Yeah, well, generally it is because, so this is interesting. In massive stars, it's driven mostly by this. When you make these observations, you see that actually mass ratios hardly go beyond 0.1, below 0.1. So it's a kind of selection effect.
Okay.
Because on the one hand, smaller mass ratios implies smaller secondaries, which may be more hard to be seen. On the other hand, it can be driven by the formation process.
Okay.
We really don't know, actually.
Okay.
Yeah. So A and B criteria are generally used in the field and are still based on observational constraints, as I said. And more or less resembles what is also found in this mass ratio distribution.
Quick question here.
Yep.
I think I missed it, but point number B, why is that the case? Why is it a random pairing?
Yeah, this is again something we see in the observation. The few observations we have, seems to be not a preference for distribution in mass ratio for small stars, while you start seeing a preferential kind of pairing for more massive stars. And this is again related to this actually, because least massive stars are well, no. Let's say that the high fraction of binaries that you see in massive stars provide us with those constraints on the mass ratio. Least massive stars seem to be paired randomly, and the reason can be in the microphysics that regulates stellar formation itself. We don't know much.
And you also don't see too many of them, I guess. That's
well, for the small one we see, but they are all evolved sometimes. So. Yeah. Okay, for the separation, instead, you either have to rely on the same major axis, or the eccentricity of the orbit, or the orbital period. Now, the orbital period of a binary is related to the same major axis through this relation, and this is the mass of the binary. So if you get the masses from the procedure we just discussed, and you get the period from something, you can get the same major axis. And something I'm talking about, again, are constraints on the orbital period distribution of massive and young stars, which is, again, compatible with the power law. So you can draw an orbital period from that distribution and then calculate the same major axis. There are alternatives. As I said, these are really uncertain models. And depending on the environment you're trying to test, that distribution may not fit your needs. So sometimes people use a logarithmic distribution. And this is based on observation of 90s in the galactic center, where you see young stars paired with a same major axis distribution that is more or less flat in logarithmic values. But you can also explore a bit the parameter space with other distributions. And for the eccentricity, again, we have observational constraints, which are based, again, on massive stars observations. Or you can have more general assumptions like that the eccentricity follows a thermal distribution. In such a case, these are predictions from very early works in the century by Jeans and by Ambartsumian that come out from the consideration that your stars are forming in a turbulent environment, so dynamics is involved. And if you make calculations when you account for many weak encounters among components of a system, you end up with systems with an eccentricity that follows this distribution. Sorry. Let's assume that you form these binaries through any of the possible choices here or choice of your own. Then you need to account for stellar evolution of these objects. Now, stellar evolution is very complex and it's a very huge topic, and we will just go through a bit of it. So, if the two stars are together, but they are far enough and separated each other far enough, they will evolve as single stars. They won't feel much the effect of the other. So they will behave as the single stars we already saw in the previous slides. But if they are close enough, they can interact. And the main way they interact is by transferring mass onto each other. And there are three main ways to transfer mass from one star to another. One is wind mass transfer, and then we have Roche-Lobe overflow and common envelope. The wind mass transfer case is, you can imagine as your star is in the main sequence, and the hydrogen in the center is gone. You have helium. The star undergoes a phase of contraction and expansion. And during this stage, you start losing mass through winds. A very simplistic way to say that. So the star is losing mass, and this mass lost is traveling away. And now, if you are a star in a binary, your companion will be orbiting around you. So the star you're losing can impact the trajectory of your companion, and some mass could be accreted on it. But unfortunately, this way of transferring mass is very inefficient, and so then we will not talk about it anymore. While the other two cases are more interesting. So the Roche-Lobe overflow is based on the fact that if you put yourself in the reference frame of a binary, in the co-rotating reference frame, you can draw around you surfaces where every point has a constant value of the gravitational potential, equipotential surfaces. And as long as you increase the value of the gravitational potential, you will find out in space these lobes that open up. Lobes that open up around the two stars. So the minimum equilibrium surface you get describes nicely two lobes that encompass the two stars. And the intersections of the two lobes is called the first Lagrangian point, is an equilibrium point. And the point is that if you push something through L1 from the first star, it will go straight to the second star. So it will be captured by the gravitational pull of the second star. Now, as the star evolves, it inflates. So its radius increases, and the mass is changing as well, but the rate at which the radius increases is larger, meaning that the star can fill up its Roche-Lobe. When it fills up the Roche-Lobe, the material, the gaseous material of the star can flow through L1 to the other star and vice versa. And this can lead to an accretion. Now, generally, this happens. It has been, so this is a very complex mathematical problem that can be solved numerically, and then a numerically fitting formula to determine when a star starts transferring mass onto the companion is this criterion by Eggleton, 1983. So this is the radius of the star over the separation of the two stars, and is a function that depends on the mass ratio. If this ratio exceeds this critical value, there is a critical value for the mass ratio by which this happens, the star can start transferring mass. Now, the important thing is that if the star doesn't do anything but just transferring mass, you have a kind of stable mass transfer process. The donor is feeding the companion with some mass. An accretion disk will likely form around the second companion, and some mass will be accreted on the companion itself. Point is that as the star loses mass through this mass transfer process, it will adjust hydrostatically and thermally. And this will take some time. Now, if the time scale over which, and of course, the mass loss due to the transfer will change its Roche-Lobe, which entirely depends on its mass. So if the rate at which the size of the lobe changes is higher, or better to say, the time scale over which the Roche-Lobe changes is long enough for the star to adjust thermally and hydrostatically, the mass transfer will proceed steadily in a stable mass transfer process. Otherwise, the star will keep inflating, and its envelope actually will engulf the other star in what is called a common envelope phase. So now you have the first star inflating, engulfing the other, and you have the core of the evolved star and the other star moving in a common gaseous envelope. Now what happens is that when you have a star or an object moving into a gaseous medium, the gaseous friction impart a friction of the object, drifting away and dragging away orbital energy to that. So the immediate consequence of the formation of a common envelope is that the two objects start spiraling in and getting closer and closer on a very short time scale. While the two objects are spiraling in and forming a entire binary, they heat up the envelope up to a point that the envelope is expelled. So you're transferring kinetic energy into the envelope pumps up, and is ejected. And now you have two possibilities, again, depending on the time scales. Yeah.
Sorry, one question. Just to make sure I understand. So what you call this common envelope, it's really two metal-rich cores inside a kind of dense hydrogen helium medium.
Yes,
Okay.
exactly. And now, if the in-spiral phase driven by dynamical friction is more efficient than the rate at which the envelope is heated up, the two stars simply collide, and you have a stellar merger. If instead the ejection of the envelope is faster than the in-spiral rate, you end up with a tight binary, and the two stars will keep evolving, as we can see in these two examples. So let me say that the two phases we just described, Roche-Lobe overflow and common envelope, are not mutually exclusive. You can have both phases for the same binary. And here is very well described. So here we have a stellar binary model for two massive stars with an initial mass in the main sequence, MS, of 80 and 50 solar masses. And then the first star leaves the main sequence, starts burning helium in the core, and enter in this mass loss transfer phase. The companion gains some mass, while the transfer peel away the outer layer of the star, leaving behind a Wolf-Rayet star. The Wolf-Rayet star now doesn't feel anymore its companion, and vice versa, and just directly collapses to a black hole. And now the main sequence star, the companion main sequence star, leaves the main sequence, inflate, but this time mass transfer cannot proceed in a stable way. You have common envelope. This is happening during the core helium burning phase. So you lost the envelope of the star. You have the two objects that immediately spiral in. Look at the times here. It's like 0.5 megayear. The two stars are brought together. The two objects are brought together, and now you have again a Wolf-Rayet that directly collapses to black hole. So after just 5 megayear of evolution, this is the time megayear. After 5 megayear, you went from two massive stars to two black holes in a tie orbit that will eventually merge in 6.8 gigayear. And here you have seen that you can go through Roche-Lobe overflow and then common envelope. And this is kind of the more common way to form black hole binary mergers through this isolated formation channel. In a more general way, you can see the same, but in that case, so you again end up here after a Roche-Lobe mass transfer phase, and then you can have common envelope and the formation of the binary, or a second stable mass transfer phase where you again can form a black hole binary pair. Okay, now we have discussed how single stars behave, how sample a stellar population, how sample a binary population of stars, and what are the processes that regulate their evolution from the star stage to the black hole stage. Okay? When you put everything together, you can initialize different stellar populations with different values of the metallicity and try to see what are the properties of the outcomes, right? So for example, here you see the distribution of primary... Yep.
So let's say the common envelope process was not efficient. You're not able to get rid of the envelope. It stays, and the things just merge. Do you expect like an electromagnetic counterpart to break through the envelope?
So this is a good question, and actually it really depends on the physics of the envelope. But the point is that we don't know how it behaves. In fact, common envelope physics is the least known process in stellar evolution. So depending on the thickness of the envelope, this will affect the possibility to form an electromagnetic transient, not only to form it, but for it to break through the envelope itself. The point is that the number of numerical... So this is something that you need to solve with magneto-hydrodynamical simulations, actually, to really catch what is happening. And there are a few. We didn't include, actually were mostly hydro simulation, where you just compute the amount of energy you're transferring to the envelope. But I don't think they made any prediction or claim on the development of an electromagnetic transient or so. It's a good question. I don't know.
Another quick follow-up is that is this probably is it a correct statement to say that common envelope is one of the biggest reasons why we expect very low eccentricities from isolated?
Yes, that is correct. Yes, one of the outcome of dynamical friction process is that, so whenever you have an object moving in a kind of sea of light particles, we would have talked about that later, but never mind. So the point is that in a very brief way to describe it, when you have an object moving through a medium of smaller objects, the gravitational focusing makes an accumulation of objects behind and forming a wake behind the motion of the massive objects, and this causes a friction. This steals away orbital energy from the object. So generally speaking, if you are in a gaseous medium, you have this kind of motion. And this happens also if your object, let's say, for example, a stellar cluster is embedded in a sea of light stars. This is, again, still dynamical friction. It's just a different kind of, also the treatment is very similar. Now, the point is that the dynamical friction time scale and the dynamical friction process, not only tends to remove orbital energy, meaning that you're spiraling, but it's also circularizing the orbit. So this means that even if you start on a very eccentric orbit, after a few cycles you will end up with something very circular. And this is a nice prediction of the isolated binary formation scenario. That is, black hole binaries formed through this channel likely have almost zero eccentricity, or very residual one. Point is that the way we model dynamical friction is based on Chandrasekhar work from 40s, and it has its own limits. So there are new implementation actually recently developed by Trani et al., 2022 or 23, where they tried to have a more self-consistent way to account for dynamical friction during the common envelope phase, and they ended up with some models where actually some residual eccentricity is preserved at the formation of the binary black hole merger, binary black hole. So it's something that is under development, let's say. But generally speaking, the canonical theory is that when you have dynamical friction, the final eccentricity of the orbit is close to zero. Yep.
Okay, so on the last slide, comparing between the common on the right hand, between common envelope and like two stages of stable mass transfer, sort of, is it representative then that like this? I guess the dynamical friction reduces the separation between the two. So, are there cases in which we expect the separation to be small enough if you have two stages of stable mass transfer where you can have a merging binary in a Hubble time? Or
so you can still have a merger in a Hubble time, and the reason is that while you're transferring mass, you are changing the orbital elements of your binary.
Okay.
In particular, you are causing, depending on how the mass transfer proceeds, you can either widen the orbit or tighten it up. So this is this critically depends on the stage of the stellar evolution and the properties of the binary when the mass transfer starts.
Okay, thank you.
Yep. So now we can simulate a population of stars, or binary stars, with a given primary mass distribution, mass ratio distribution, orbital period, eccentricity, metallicity. We can provide this list of stars, binary stars, to our favored stellar evolution tool that will transform them into black hole binaries and will tell us which one are going to merge within Hubble time. And then we can, for example, look at the distribution of the primary masses of black holes. These are black holes that are going to merge within Hubble time, and this is the primary mass. An interesting thing here is that this is the outcome of just the isolated binary formation scenario, right? So metal-rich environments, which are the lighter colors here, tend to form smaller black holes. The same we saw actually at the beginning of the lecture, right? So generally, metal-rich objects like the sun, like with the same metallicity of the sun, are going to produce black holes which are around up to 20, 25 solar masses. The more metal-poor stars in a binary population instead can form more massive black holes, yet the maximum mass they can attain is around 60 to 70 solar masses. So we started like dipping into the upper mass gap, but we are not really into that. Because remember, the mass gap is from 60 to 200 something, right? So the isolated binary evolution is not enough to explain upper mass gap objects. Well, whatever. Now, if we want to make predictions for a detector like LISA, this is yet not enough, because now we have just populations that are discriminated by, or, well, dissected into different values of the metallicities. But now, how do we convolve these populations with the cosmological evolution of the universe? We need to make assumptions on how stars form over cosmic times, and how the metallicity, at the very least, how the metallicity of stars evolve toward time. And a generally assumed approach is that you rely on the cosmic star formation rate derived by observations of galaxies and quasars up to a redshift of 8 or so. So this is a work by Madao and Dickinson 2014, and then Madao and Fragos 2017. That relation tells you the amount of mass you form per year and per cubic megaparsec. So this is telling us how many stellar material is produced every year per cosmic beams, if you want, different redshift beams. Now, we also know that at the beginning, at the very beginning of the universe, the first stars that had formed were almost metal-free. And now a metal-free star starts burning hydrogen, helium, carbon, oxygen, whatever, and start producing a heavier element. And then they explode, releasing this heavier element into the medium, so then a new generation of stars will form with a higher metallicity. And this goes on and on and on. So this means that from redshift 15 or 20 or whatever to smaller redshift, the average metallicity must increase. And generally, the assumption is that the average metallicity increases with the redshift through a power law. This is the average increase. And then you can make assumptions on what is the distribution around this average value. A generally assumed distribution is a log flat distribution, you see there, and log normal distribution, sorry, with the mean value and some dispersion. Dispersion is very uncertain, so you can find out in literature values from 0.1 to 0.7 or so. And this is the easiest way to model, to, let's say, attach to every redshift bin a population of binary stars with some metallicity. So now if you take these catalogs of black hole binary mergers and you convolve them with this evolution, you can know somehow how these objects are distributed across cosmic times, and then you can use them to make predictions for observation, for example. But we didn't make it yet. So we've seen that the star formation rate is some function. Let's call it star formation rate. Now, we have seen that a different redshift, sorry, this is at Z. A different redshift, the probability for an object to have a given metallicity is something like, this depends, this is roughly this one, right? So this tells us how much stellar material is formed with a given metallicity at redshift zeta first, right? Now, out of all those objects, some of them will merge at some redshift z. How many of them have formed at zeta first with metallicity z and will merge in z in a different redshift? Let's say we want to calculate how many mergers are here, right? In this redshift here. To know this, I need to know the history of the stars that have formed at different redshifts, right? So I need to go in zeta first and calculate how many of them formed here, merged here with different metallicities. So this is this number. Now, since here we are calculating the amount of mass, the stellar masses produced, I need to transform this into something that scale up with this. And generally what we do is to divide the number of mergers we get by the amount of stellar material we simulated. So, simple assumptions. I want to model my population of binary stars. I simulate, I don't know, 1 million solar masses, which will correspond to n binaries. Those n binaries are evolved, and this is the result. So the number of final mergers is divided by these 1 million solar stars, and this gives me a merging efficiency. The merger efficiency is exactly this number here. And generally, for us, these numbers comes from simulations. So, okay, this is not enough yet, because then we have to integrate this over cosmic times. So we need to know, yeah. Yep, and then to get a rate out of this. So now we have something that is solar mass per time unit per volume unit, multiplied by time, multiplied by the inverse of a mass. So this is 1 over cosmic volume. And we need also to divide by the interval of time in Z during which these mergers are happening. Here, I want to calculate what is the merger rate at redshift Z. So this is the interval of time during which merging are happening. So I have the number of objects that are merging in such interval of time. And now if you integrate over all the values of the metallicity and over zeta first, which goes from zeta to, let's say, zeta max, you will get the merger rate densities at a given redshift. So this is the way to convolve populations and star formation histories to get a rate. And this is more or less summarized here. And these are results from Yorio et al. 2023, the reference, for different stellar evolution models with different approaches in modeling the common envelope. This is generally quantified through this quantity here. We won't go much into detail. Bottom line is that you can do this for black hole binaries, for binary neutron stars, for black hole neutron star combination, whatever you want, and you can get rates. And you can compare your rates with what you just see now, for example, with Ligenberger. So this can help you placing constraint on the physics of binary systems. As you can see here, for example, orange and pink lines are out of LVK predictions, if you want, while purple one agrees more or less. And then you can do this for every kind of model. Now, if you have this, and you have the distribution of masses or semi-major axis, whatever you want, of the population, you can use the rate and the population to draw actual samples that will resemble the population of black hole binary mergers coming out from our model, our mock universe. And this is how the distribution of primary and companion mass look like for just the isolated binary formation scenario. And that is just a scatter plot showing M1 and M2. Sorry, I forgot the label there. So you see that the primary mass has some peak, but bottom line is that still you cannot go beyond 50 solar masses. So this is what you get with our mock universe. Now you can keep them. You can repeat the same for white dwarf, for neutron star. You can take them and think, okay, are we going to see them with LISA? So you can, for example, assume that your black hole binary, so these are black hole binaries again, are still far apart, 100 years to the merger, so they will appear as stationary sources in LISA. You can calculate the strain, whatever you want, for different values of the redshift. And you immediately see that actually, even getting closer to us, 100 megaparsec is very close to us, you can just get a glimpse of these black hole binaries from the isolated binary evolution scenario with LISA. And even though you manage to get a subsample of binaries that is going to merge within the LISA observation time, still you need to be extremely close to see them with LISA. So this is extremely challenging, and indeed, the number of objects that of this kind of object that LISA is expected to detect, I think, is of the order of 10 or so, something like that. Okay, so 100 megaparsec is close enough, but it's not the closest possible distance, right? We could also have black hole binaries in our galaxy. So this means within a distance of 100 kiloparsec. Now, as you know, the strain scales with the inverse of the distance. And so you can repeat the same exact exercise for black hole binaries, neutron star binaries, and white dwarf binaries within our own galaxy. The extent of the Milky Way is around 100 kiloparsec. The total mass is around 6 times 10 to the 10, 10 to the 11 solar masses. And according to the fraction we have seen at the beginning, you can more or less make an idea of how many of these objects we could have in our own galaxies. So this is a bunch of binaries that are 10,000 or 10 million years away from merger, but are orbiting our galaxy. In this case, if you repeat the same exercise, you can see that stellar black hole binaries actually can be detected with a signal-to-noise ratio of around 100 in the most best scenarios. But also neutron star and white dwarf can be detected as well. And remember, white dwarfs are going to be much more frequent in our stellar populations than black holes. And indeed, there is a big chunk of people in LISA working on galactic binaries, right? And this is one beautiful plot that is in the LISA white paper, where the sensitivity also, I just forgot to mention, while these are going to be resolvable sources at some extent, all those in this region here will merge together, their signals will merge together to form a foreground, right? And this is something that people have been working a lot about, and is shown here. This is the galactic foreground of objects in LISA that cannot be resolved, but still contribute with a signal that is going to be represented like a kind of noise in the detector sensitivity. And what you see there actually are different population of compact binaries in the galaxy, black holes, neutron stars, and white dwarfs. So this big chunk of objects is white dwarfs. And the red spots there are very interesting sources because they are called verification binaries. They are like 24 or so binaries that contains white dwarfs, and we saw them through electromagnetic signals, right? So we know them already. Yep.
Sorry. I should have asked this question because we've seen this graph before, but I'm just confused with this cloud. Do we expect each gray point to be identified?
This one you mean?
Yeah. All of these points in
So these in principle are resolvable sources.
Okay.
So the point is that you see this gap here, because from here upward, all sources have a signal-to-noise ratio above 7.
Okay.
So they are deemed to be resolvable sources. And in the galaxy, you would expect like 10,000 of them.
And then the foreground is this wiggly blue line.
This one instead are binaries that are farther away, or they are more separated apart. So their signal is too low to be detected and resolved, but still will contribute to the overall foreground of sources we have. And now, so this is how stationary sources will look like in LISA from the stellar population, from stars, let's say. And then these blue tracks here are the few black hole binaries that are expected to significantly evolve over LISA mission lifetime. So we will see glimpse of their evolution or big chunk of the evolution, depending on how far are they from merger.
Sorry?
Yep.
I saw that there were like a bunch of the black hole binaries that were in between the white dwarf. Would be able to resolve if they are
well,
white dwarf
in principle,
or black
everything
holes?
is shown here is resolvable.
Yeah, but could we be able to distinguish the
This is a good
sources?
question. This will depend a lot on the way we will do parameter estimation, right? So we will get the signal. Now, how good are we at discriminating between different sources? In principle, we should do. But it will depend a lot on the techniques that will be applied to the analysis of the data we are getting from.
And
in principle, we can.
May I also ask then, what is the gap between the galactic foreground and
This one?
the cloud? Yes.
So this is because everything is below, as a signal-to-noise ratio below 7, roughly speaking. So below 7, you wouldn't expect to resolve them as a single sources. That's just why.
And so doesn't that count as foreground as well? since it's not
Indeed,
resolvable?
indeed. But the net effect is this one.
Okay.
Because then there are many more sources here. Okay, so this is just a bit of addiction, right?
Okay.
I mean, they sum up, but... Yep.
Hi. So I have a question. What is the F dot threshold between considering a source to be stationary and some to be actually moving within the LISA timeframe? Because I see some very, very short blue tracks that almost look like dots, but I think are actually evolving. So what's that threshold?
So for the LISA white paper, I don't remember if this is assumed to have a mission lifetime of 10 years or 4 years. But the point is that any time the binary frequency change or the binary orbital properties change within the observational lifetime, you will see a track. This is the point. And generally, these objects are objects that have merging time of, I would say, maybe 20 years or so. And some of them are surely merging within the LISA lifetime.
Okay.
Yeah.
Okay, thank you.
Yep. Okay. So another way to make prediction on the detectability of objects at different distances is through the horizon redshift or the luminosity distance redshift. So this plot tells us for a binary at a given emitting gravitational waves at a given frequency, how far we can spot them with LISA for different values of the emerging time. More clear example. Let's assume we have a binary with masses 10 plus 10. So this is the purple line here. And our binary is 1 megayear apart from merger. This means that to spot it with LISA, with a signal-to-noise ratio of at least 7, we can go up to 10 to the minus 2 megaparsec. So 10 kiloparsec or so, right? So this means that you can see this kind of object, such wide binaries, just in our closest vicinity. Keep in mind that the center of our galaxy is 8 kiloparsec away from us. So this is really local, a local portion of the galaxy. And the interesting thing is that as long as you remain in the domain of white dwarfs, neutron stars, or black holes, you remain limited to the Virgo cluster. This is still local universe, still a bunch of megaparsecs away. So to really have a glimpse of what is happening in the cosmos, you need to go to higher masses. And in fact, you see that the first gravitational wave ever detected, 150914, could be detected also by LISA, at least in the last phase of evolution, up to 1 gigaparsec or so. Point is that where are they coming from? Because single and binary stellar evolution are not enough to form those kind of binaries. So the reason, yep.
Just very quickly, you had shown us a plot before, so that means I can ask this question. What is the most popular theory for alpha, common envelope efficiency greater than 1? What does that even mean?
Oh, that's a good question. So alpha regulates the amount of energy you input into the common envelope. So we talk about the evaporation of the envelope. And the way you evaporate the envelope is generally parameterized to this common envelope parameter alpha. So alpha equal to 1 means that you are practically destroying the envelope. You are transferring all the mass you need to erase it, to eject it. Less than 1 means that you are transferring some energy, but there is some dissipation in between. Larger values means that there is some extra source of energy that not only make the envelope evaporates, but it does it on a shorter time scale. Now, the reason why an alpha common envelope larger than 1 should exist is unclear. But the good point is that actually, the models that best represent what we just see now are assuming an alpha common envelope between 1 and 0.5, which is more reasonable because it means that you are using more than 50% of your energy reservoir to evaporate the common envelope. Okay, so this is a relatively good assumption, but still it's not enough to produce massive black holes. And so we need to resort to other formation channels. And the other one is the dynamical formation. So now Up to now, stars were in a galactic field, chilling in the galactic disk, moving around. Nobody was, harassing them. Now let's move in a crowded space. In a star cluster, you have 100,000, if not million stars packed together in a 1 parsec, right? So for a comparison, consider that our closest neighbor is Proxima Centauri, and this is like 4 light year from us. If we were in a globular cluster, the amount of stars would have been like 10,000 larger, and the density inside would have been 10,000 larger than what we have here in our galactic neighborhood. So densities are so high that stars frequently interact with each other. And interactions can drive the formation of binaries, can drive the formation of intermediate mass black holes, and the formation of IMBHs plus stellar black holes that can merge within about time. These are called intermediate mass ratio spirals. And occasionally, some star clusters can fall toward the galactic center, again because of dynamical friction. So a star cluster moving in a galactic field slowly loses orbital energy and drifts toward the galactic center. Now, if a star cluster forms at a distance of around 100 parsecs or so, and we have evidence of star clusters in the galaxy at those distances, they would drift into the center of the galaxy in a relatively short time, meaning that you are on the first, you are increasing the amount of mass in the nucleus. Now, if your cluster formed an IMBH, you are bringing your IMBH in the galactic center, where it is likely to find a supermassive black hole. And you can form IMBH supermassive black hole binaries, which are called heavy IMRIs, or again, IMRIs. I mean, this light and heavy IMRIs is something relatively new. Now, to understand how dynamical formation form, we need to know what kind of star cluster environments we can find out there. And there are different types of clusters. So this is a real image taken from Sardinia, not by me, unfortunately, but it's a beautiful one, that shows you different flavors of star clusters that we can see. White one are called open clusters. Blue one are globular clusters, and the red circle there is the galactic center, where a nuclear star cluster is also found. Open clusters are generally sparse and loosely populated objects which contain up to 1,000 stars or so. They are found in the galactic disk. They are pretty young, and we observe them young because actually their lifetime is pretty short. Because being so sparse, they are shattered by the tidal field of the galaxy and destroyed over time scales of around 100 megayear or a few gigayear at most. So the only one that we can see must be young, otherwise have been destroyed. And we see them, thousands of them, in the galaxy. Let's just be a bit faster on this. Globular clusters instead are massive objects. We observe the Milky Way. We observe them around a number of around 200. They contain up to a few million stars, and they are very, very old, 10 to 13 gigayear-old objects. So they are the reminder of the first formation bursts in our galaxy, possibly. And they provide us with a clean view on what is the outcome of stellar dynamics, because they're very old, so they have been processed a lot of stellar interactions. We don't know where globular clusters come from, but we think they come from what we call young massive clusters or superstar clusters, which are very young, like a few mega-year-old object, containing up to 10 to the 5, even 10 to the 6 solar mass in stars, and they have been found in star-bursting regions, so regions where the formation of stars is intense. They may be the progenitors of globular clusters, but we really don't know. But they are interesting objects because the dynamics there also can proceed quite well. And then in the center of galaxies, like in more than 60% of galaxies and the Milky Way too, we observe a nuclear stellar cluster. These are the most dense stellar system in the universe. They can contain for example, our own Milky Way nuclear cluster contain around 30 million stars, and all packed within 1 to 2 parsec. So densities are above 10 to the 6 solar mass per cubic parsec, and they often contain in their center the harbors a supermassive black hole, like it is happening in our galaxy indeed. So these are very interesting objects. We don't know much about how they did form, but there surely are sites where dynamical interactions can proceed. Now, how dynamical interactions develop in a star cluster and how they affect the overall evolution of the star cluster is described through what is called the relaxation process. And let's see if we can just go through this because it's a bit late. So let's assume you have a star in a stellar system traveling, and at some point is going to have a flyby over another star. So this is geometrically what is happening, right? Now, before and right after the flyby, the force felt by the incoming star will balance itself, right? So the parallel component of the acceleration impinged on the flyby star will be, on average, 0. But what is not 0 is the perpendicular part of the force, right? So now the this component geometrically is just, let's assume that the two stars have similar masses. So we have a component gm squared, and then we have the distance between the two objects, and then we have the cosine of theta, which is just b over r, right? And r again is just, sorry, this is like this. So then will be something like this. And then you can still write it as, the amount of space travel through during the flyby, x will just be the velocity of the star times the time of flyby. So we can rewrite this like now the variation in velocity impinged on the star will roughly be given by the integral of this force let's assume we are in a kind of unperturbed situation where we start from some minus infinite time and we travel through. Now the interesting thing is that you have here g m, this is a square, sorry, over b square. And then you can replace vt over b with a variable s, meaning that the t is equal to b over v, the s. And then you get like this, and then you have 1 plus s squared minus 3. Exactly. And now, interestingly enough, if you just substitute s with the tangent of another variable, this integral gives you 2. So the variation in the velocity of the star after the flyby is twice gm over bv, where v is the velocity of the star, b is called the impact parameter, and m is the mass of the star. And the minimum distance you can, the minimum impact parameter you can attain is the one for which the change in velocity equals the initial velocity of the star. So the v over v is equal to 1. This means, if you do the math, is just you can define a b min, also called b90 parameter, which is just right. So when the impact parameter reaches this value, the deflection is, let's say, a 90 degrees deflection, and this means that your star completely loses information about its previous traveling properties. Now, the average of this quantity is 0, because, I mean, this is random encounters, but the square of the variation is not, and you can calculate it as here, a summation of all the square values of these changes. And now this can be simplified into a single variation times the number of encounters that you make, assuming that each encounter will impinge on you at the similar value of this delta V value. Now, the number of encounters, instantaneously speaking, can be calculated as the surface density of perturbers in a given annulus between an impact parameter of B and V plus dB. So if we assume that the surface density of perturbers here is n over pi r squared, where r is the size of your cluster, this will be the number of interactions you get. Well, yes, you have to integrate over the. So you can multiply the number of encounters by the single variation in velocity, and then you can integrate that to get the average mean square velocity. And this gives you a nice relation. Let me see what time is it now. Yeah, let's be a bit faster on this. So the nice relation can be converted into a time scale. Okay, the time scale over which stars will lose their information, their initial conditions, and this is called the relaxation time. So over a relaxation time, a cluster, the stars in the cluster, will undergo interactions. And if the relaxation time of a star cluster is longer than its age, the cluster is not collisional. Interactions didn't have time yet to take place. But if the relaxation time is shorter than the cluster age, it means that interactions happened, so the object is collisional. And these are the typical values of the relaxation time. For a young cluster, the relaxation time can be as short as a few mega a year. For a globular cluster, it can be up to a few giga a year, to give you a reference. Now, let me just say, relaxation implies that some stars gain energy, some stars lose that. Now, if you have a real stellar population with stars with different masses, relaxation is something even more violent, because the most massive stars, which are now moving in a sea of lighter objects, will experience dynamical friction again. So the most massive stars will drift toward the cluster center while interacting with other stars, and transfer energy, to the lighter component. This leads an accumulation of massive objects in the central part of the cluster and lighter objects in the outside. And this is called mass segregation. So over relaxation times, you will have mass segregated clusters where the most massive objects are in the center and some of them are outside. While this is happening, this is a kind of catastrophic process by which the exchange of the energy loss from massive stars is not balanced, never. And the core of massive objects keep contracting while expelling lighter objects. So you have a phase in cluster lifetime where you have a core contraction, density rises up, and formally this can proceed indefinitely up to the collapse of the core. So this is a phase called core collapse. Core collapse for a realistic population of stars occur in a fraction of the relaxation time. So it's a very violent and powerful event that is eventually contrasted by the formation of binaries. While the densities keep rising, objects keep interacting, at some point some of them will pair, and now as a binary they will act as an engine that pushes energy into the core. A binary and something coming in a binary single interaction. What is generally happening is that the perturber will gain energy while the binary will lose energy. So this is shrinking and this is ejected away. This is a way to inject energy into the core and halt the core collapse. So the cluster will undergo a phase of contraction maximum maximum density, and then rebound and expand again. And at core collapse, a lot of things can happen. Now, if the core collapse time is short enough, this can happen when massive stars are still stars. For example, in open and young cluster, the core collapse time is of the order of 7 megayear at most. So this means that the majority of massive stars will still be stars when the collapse happens. While for most massive objects, collapse happens on a longer time scale compared to the stellar evolution time scale. This gives you two possible outcomes. One are clusters where the core collapse time is short. And these are generally, so here there is a bunch of observed star clusters with masses and half mass radii, typical radii of the star cluster, and these tiny lines here represent the relaxation times, which is this region here contains clusters whose core collapse time is shorter than the typical time style for stellar evolution. In this case, interactions can trigger different funny outcomes. Two stars can collide together and form a more massive star and mix up their structure. Or you can start forming binaries. You have a binary and a perturber, and then you have an exchange in the components. You can trigger mergers between the impactor or perturbers and one of the binary components. And then at some point, you can start forming some black holes. So you can also end up with a collision between stars and black holes. The consequence of these effects is a clear impact on the black hole mass spectrum. So in black, in this particular model, again, we have the initial to final mass relation. In black is what you get from single stars. And in red is what you get from a population of single and binary stars put together in a star cluster. So the idea is, let's take 100,000 stars. Some of them are paired, some of them are not. Let's put them in a star cluster. Let's the star cluster evolve through dynamics, weight relaxation time, and let's have a look at the population of black holes after that. Some of those binaries end up merging, and before becoming black holes, of course. And the new star has a structure that helps them preventing peri-instability supernovae. So you find some black holes in the gap. Some of them simply have masses which are more scattered compared to the prediction of a single stellar evolution model. So dynamics is fundamental in determining and broadening the mass spectrum of black holes. And another interesting outcome of these interactions is that you can actually pile up many stars and merge them continuously if the cluster is particularly dense. So these are results from numerical simulations from a PhD student in Garching, where 100,000 star clusters have been simulated with quite high densities, and at collapse, which is happening at around 0.2 megayear, one of the stars with an initial mass of around 30 solar masses, the one that follows the blue track, underwent a collision. Oh, sorry, I just stopped. Yeah, underwent a collision there, and then started colliding with many other stars, up to a point where another star that were undergoing some collisions pair up with our primary blue star, sorry, and the new star keep evolving and merging with other objects till it form a black hole and collide with another one, forming a final black hole of around 300 solar masses. So this is called like a runaway formation scenario for intermediate mass black holes. Many stars merging together, forming a final black hole that is way beyond the upper mass gap. And this is another example where you have initially a binary and another object coming in. These are from Dragon 2 simulations, which we developed a few years ago. And the perturber actually merged with a secondary in the binary. A new binary is formed, another perturber comes in, another merger happens, and then a new star leaves the main sequence, inflates, and engulfs the other one, actually swallow the other one, and form a very massive star that then form an NBH. So in such clusters where core collapse times are short, you can form IMBHs this way. Let me just go through that. And the typical mass of these black holes is around 100 or few hundred solar masses. It is very hard for such clusters to keep them inside the cluster, because a few hundred solar mass, still the black hole can undergo interactions with other massive black holes of 50, 60, 80 solar mass, and get a recoil kick, a Newtonian recoil kick, large enough to eject it from the cluster, preventing it from further growing over time. Older systems, where the core collapse happens on longer time scales instead, will undergo mass segregation and core collapse after black holes have formed. So now the evolution is a bit more complicated indeed. What is happening is that black holes gather in the center, so you have a first phase of contraction and the formation of a black hole subsystem. Black holes are the most massive objects in the cluster, so they are going to dominate dynamical interactions because their cross-sections are larger than other stars. So you have a contractions phase where black holes transfer energy to lighter objects and gather together. And then a maximum density peak is reached. Binaries start forming and the core rebound. And you have a kind of balanced evolution phase where stars transit inside this black hole subsystem and then are scattered away again. And then you have a second core collapse phase. And then most of black holes during the second phase are ejected away, because, again, density rises up, interactions become more violent, and objects are ejected. And then you have this kind of stable evolution. And the main outcome of this evolution is to trigger the formation of black hole binaries that routinely merge either inside of the cluster or are ejected in a tight pair that merge outside of the cluster after a while. And here what you see is M1, M2, or M1Q distribution, Q is mass ratio again, of black hole binaries formed through dynamical interactions in star cluster models. And an interesting thing is that through dynamics, you can form something you couldn't form in isolation. For example, black holes with masses in the gap that are merging, IMBHs with a mass above 100 solar masses, IMBHs with a companion that is fairly massive and falls in the gap as well. This is possible just if you account for dynamics. Now, to try to reach the conclusion and not be too long on that. One thing that is happening for black holes, they merge, they form beautiful black hole mergers, but after the merger, they receive a gravitational wave recoil that can be as large as 10,000 kilometers per second, which is way larger than any escape velocity from any realistic star cluster. So most of the products of black hole binary mergers are going to be ejected from their host environment. But if they receive a kick which is small enough, they will be just pushed out of their central orbit and will move on wider orbit and come back owing to dynamical friction again. Now they are more massive than the average black holes in the system, so they are likely to pair up with another black hole and possibly merge again. And of course, this goes on again and again. And this is what is called the hierarchical black hole merger scenario, which is nowadays used to explain many features of some of the sources we observe today. The bottom line is that the hierarchical black hole formation scenario may be crucial to explain some of the massive black holes we see today. Because imagine you are at a redshift of 20. First stars are forming, first black holes are forming, core collapse happens, black hole starts merging together, you form massive seeds. And now if you are in the center of a galaxy, these massive seeds that can feed on the gas in the galaxy and grow farther and farther, possibly growing up to supermassive black hole scales. And this is something you will hear more about in the next astrophysics lecture. So if we proceed with the same way we proceeded for isolated binaries, we again make our model and calculate dynamical interaction effects, and then we calculate the terminal mass of the black holes in a merger, we end up with this kind of distribution for different metallicities. So you see that dynamics can form, this is again the primary mass of the black hole, and you see that dynamics can trigger the formation of black holes as massive as 10 to the 4, 10 to the 5, and even 10 to the 6 solar mass actually. And now if you filter that out with the line of reasoning and arguments we made for the calculation of the merger rate, you can again draw samples from these general distributions according to the merger rate of our mock universe, and you get the final cosmic population of merging IMBHs. And now we can take them and again see if they're visible with LISA. And again, we did the same exercise, 10 to the 3 plus 30, 10 to the 4 plus 30 binaries, solar mass binaries. You see that, again, it's very hard for us to use LISA to distinguish cosmic population of IMBHs. We need to rely on other detectors. And this is also shown in the horizon redshift now. So this is the maximum redshift. We can see a source with a given redshift, with a given signal-to-noise ratio, sorry, for different values of the primary mass and different values of the companion mass. So you see that if you form 1,000 solar mass black hole plus a 10 solar mass black hole, you really cannot go exploring the deep universe. The redshift is 0.1, still more or less local universe. And to go cosmological, to have a cosmological reach, you need to push the mass of your black holes down to the maximum limit and also the mass of the companion down to the maximum limit. So this gives us an idea of how a detector like LISA can be used to explore the local universe for low mass IMBHs and the cosmological reach for more massive IMBHs. And the interesting thing, and I'm going to conclude right now, the interesting thing is that IMBH black hole binaries are multi-band sources, which means they start in spiraling in millihertz frequency band, and then they will sweep through decihertz and sometimes hertz. So they could be possibly observed with LISA, with high-frequency detectors like Einstein telescope, and also with decihertz detector, which are those detectors that are going to be sensitive in between 10 to the minus 2 and 1 hertz or so. So this means that, for example, for a typical source, this is a few hundred solar mass source, you can start in our galactic backyard, basically. You can start seeing that 4 years before merger with LISA, and then we'll transit through this range where detectors like the SIGO will be sensitive, or the Lunar Gravitational Wave Antenna, and then it will end up in Einstein Telescope or Cosmic Explorer or LIGO Virgo. So this is something that would be very interesting to see. And let me just conclude here saying that you can form also IMBH binaries. This is way less probable, because to form one IMBH in a star cluster, you need interactions, right? But interactions are monopolized by the object that is growing the most. Meaning that if you start growing IMBH, it's very unlikely you will grow another IMBH in the same environment. The only way to get two IMBHs getting together is to get two clusters and merge them together. And we have evidence of many interacting clusters nowadays in galaxies, which can help forming IMBH binaries. Still, they are multi-band sources. They are louder sources in LISA compared to IMRIs. And I find this plot very interesting because it shows actually the reach, the cosmological reach of Einstein telescope and LISA for binaries with a primary mass, with a total mass on the x-axis and a mass ratio identified by different curves. So for a fixed signal-to-noise ratio. And if you look here, it is clear that LISA cannot do much about these stellar mass binaries. But if you look here, this is an exciting place where Einstein telescope and LISA can work in synergy to unlock and unveil the properties of these black hole binaries that may be composed of a proper and solid IMBH and still some kind of stellar companion, like in this case. This orange one is for a mass ratio of 0.1, so it's 1,000 plus 100 or so. And again, and you can see both with LISA and a T. Even though it's like a redshift of 2, this will give us a glimpse on how this object forms. Okay, I think I will stop here.
Yeah, thank you very much. Maybe just in the interest of time, if you have any questions, ask them during the coffee break. Let's have the coffee break now, and let's reconvene in 15, 20 minutes. Try to get your coffee quite fast so that we're not too late for lunch.